Well, good morning. This is 11:32, 2 minutes late getting started on the 18th of February, 2020. It's supposed to be a linear algebra class, and right now the bad news is I'm the only one in the room. So hopefully the others will be coming soon, but I'll go on and get started. I will hold off doing the announcements until somebody is physically in the room to hear the announcements, but other than that, I'll get started. Now, where we left off last time, we finished section 2.2, and we're just getting ready to start 2.3. I don't have a mark that we did anything in 2.3, so we'll be starting there from scratch. Now, section 2.2, quick look back, discuss some of the similarities between algebra of real numbers and the algebra of matrices. There's some differences, some similarities. This section further develops the algebra of matrices to include solutions of matrix equations involving matrix multiplication. So let's begin. Consider the real number equation AX is equal to B. Pretty simple equation. Let me get my pen set up. Okay, AX is equal to B. Really simple equation. Okay. To solve that equation, what I like to say, divide both sides by A, okay? Which is correct. But like the book is saying here, they're saying let's multiply both sides of the equation by A to the minus 1. Now there's a reason they're doing that. So that would be A to the minus 1 times A times X is equal to A to the minus 1 times B. Now that's not how we usually write it, because A to the minus 1, anytime you have a number or a variable to the minus 1, that means reciprocal, okay? And 1 over A times A is 1. And then this would be X is equal to B over A. That's what we would have gotten the other time. Okay? So we'll leave it like that for right now. That means B over A. But in a sense, that's a reciprocal. The A to the minus 1, I call it reciprocal. They call it a multiplicative inverse of A, because A to the minus 1 times A is equal to 1, the identity element for multiplication. That definition of a multiplicative inverse of a matrix is similar, okay? But it's not reciprocal, okay? Get that in mind. Multiplicative inverse of a matrix is not the same as reciprocal of a matrix. It's a multiplicative inverse. So here's the definition for the inverse of a matrix, okay? I think I will erase what we've got here so I can start writing on a clean slide. So let's do that. So, in order to have an inverse, a matrix must be square. Just being square doesn't guarantee it has one, but it can't have an inverse if it's not square. So we start with an n by n matrix. Okay. Then there's two words. It's called, first, invertible. In other words, it does have an inverse. That's what invertible means. Here's the other word for it, non-singular. Okay? Means the same thing. Okay? Just a little bit weirder word. Okay? It's invertible or non-singular when there exists another n by n matrix n by n matrix we'll call this one B, such that A times B, now here's the weird part, is also equal to B times A, and not only are they equal, but they're equal to the identity matrix of dimension n. Okay? So most of the time, remember, multiplication of matrices is not a commutative process most of the time. However, when you have a matrix B that is does commute with A, and when it commutes, it always gives, whichever way you multiply them, gives you the identity matrix. Then, where this is the identity matrix of order n, I'm not going to write that down. That matrix B that we just described there is and they put in parentheses multiplicative, okay, inverse of A. After a while, we're not going to call it multiplicative anymore. We're just going to call it the inverse of A. Okay? A matrix that does not have an inverse is called non-invertible or singular. Okay, so notice invertible is non-singular, non-invertible is singular. Okay. Non-square matrices do not have inverses. You cannot take the inverse of a matrix that is not square. Okay? So don't even try. And one of the reasons is if A is m by n, that would mean B would need to be n by m, okay? So they're not the same size. If m is not equal to n, okay? So the product of those two would be an m by m, but the product of B n by m times A, which is a m by n, would be an n by n. So they couldn't possibly be the same if m's not equal to n. No way, okay? And here is the next theorem, and I think I'll do this on a clean page, okay? All right. If A is invertible, okay, A is an invertible matrix, then its inverse is unique. That means you can't have two different inverses out there for a single matrix A. The inverse of A is denoted by A inverse. That doesn't mean 1 over A because we don't even know what it means to be 1 over a matrix. We don't have matrix division or reciprocation or anything else. This is a definition of an inverse matrix. We use the same kind of nomenclature as we did for multiplicative inverse of a matrix, but that doesn't mean reciprocal in this case. So, here's how these proofs go, and this one's pretty easy. So it was given that A was invertible, okay? Okay. What that implies is there is some inverse, A inverse, such that A times A inverse is equal to A inverse times A, and both of these are equal to I of the same dimension they are, okay? Now, that's what it means to be invertible, okay? Let's just imagine that there is some other matrix C if there is some other matrix C, another inverse C that is not equal to A inverse, okay, then AC would equal CA, and that would also be the identity matrix I. Okay? So what you have to show is that AC and that C and A inverse have to be equal, okay? Because these two things have to be true. So if A times A inverse is equal to I, then we can multiply C times A inverse, and that would be C times I, right? Okay, but we just said that CA is the identity matrix from here, and the identity matrix times A inverse is equal to C times I. Well, anytime you multiply identity matrix by a matrix, that comes out being A inverse, and that same thing here would have to be C, and therefore can't be. Oh, perfect attendance. Half a little late, but still better to be here. Okay. All right. Now, I'll turn on projector. Got started already, so you'll have to go back and listen to how we did get started. While that's coming up, here's one new announcement. I can't remember, you may have heard this one, but it is new for this class. I doubt if either one of you are interested. If you are, please take advantage of it. But you may know someone who might be interested. Lawson State Community College has a program here that we call Office of Workforce Development. So we put on courses, classes, whatever the market needs something. If they want us to run a class for them, we'll run it for them. Okay? Of course. And here's one that we're in partnership with Alabama Power and various other utility and contracting companies. They need more line workers, okay? This could be phone company, it could be the smaller utilities, it could be companies that contract with Alabama Power, the phone companies, whatever. That's who we're doing this for, okay? Here's the program information. Here's the bad news. Applications are only being accepted today and tomorrow. They've been open for a while, but I didn't get this until yesterday, okay? It probably was out there earlier, I just didn't see it until yesterday. The training duration actually starts June 8th and goes through August the 14th, okay? The class will be meeting Monday through Friday for those 9 weeks, Monday through Friday, 8 till 4. So full 8-hour days, probably have an hour break for lunch or something like that, but Monday through Friday for 9 weeks. So it's a pretty intensive program. The program tuition is $4,150 plus fees. Now the fees include your books, any books you might need, also PPE, and I'm not absolutely sure what that is. Professional something education. Personal protection equipment. Say again? Personal protection equipment. Excellent. Personal protection equipment. Any of that you might need, you have to buy on your own, or rent or whatever. So the fees for that. You also have to take a physical exam for the commercial driver's license, so you'll be getting that as part of the course. So you have to pay for your physical. You also have to pay for any permits or licensing and exam fees that you'll be taking at the end. But the good news is scholarships are available. That's, it to me, indicates they're hurting for people, so they've come up with money to help people cover this. Whether they're going to be full scholarships or partial or what, I don't know, but some scholarship money is available. The program outcomes. If you complete the program, you'll be OSHA 10 certified. I don't know exactly what that means. I know OSHA is Occupational Safety and Health Administration or something like that. And OSHA 10 sounds pretty high certification to me. That's probably one of the fees you pay for certification, or licensing or whatever. You'll also get your commercial driver's license, because these folks have to be able to drive these lift trucks, and the lift trucks require commercial driver's license. So that's part of the thing. That's a valuable thing to have no matter what. Of course, you can probably get it for a lot less than $4,000, but you'll have that in pocket, in hand once you complete. You also receive cardiopulmonary resuscitation training, CPR training. So that's another good skill to have. And of course, you'll, at the end of this, you'll have the basic line worker skills, so you'll be able to proceed to become a line worker. Contact information here at the college is the Office of Workforce Development. Dr. James Gray is our Workforce Development Manager. He's probably set this thing up. It has a phone number for him, and since it's the 3519 is the last 4 digits, I think that means it's on this campus, because this campus, the phone numbers usually end in 35 blah blah. Okay, my number is 3435. Mine's 3449. This is 3519. So, or you can email him. There's also Mr. Tommy Hobbs, who's the Assistant Dean for Workforce Development. He's probably been involved in setting this up. But the deal is you apply through a link. And this is eventbrite.com. And then you have all sorts of symbols in there, but you also have pre-apprentice power line worker application tickets. And then some numbers and dashes and other things too. So you need to register online. So if you know of anyone who might be interested in a pretty good paying career position, okay, you might want to let them know, because this, you will certainly get your $4,150 back pretty quickly once you're hired. And it sounds like they're hiring. So take advantage of it. Let people know. All right. We started, any questions on anything before we get started today? I've already gotten started. We started in 2.3, which is inverse of a matrix. So I've already done page 62 and the very top of page 63. Okay? I didn't quite do it the same way they did, but very, very close. And it was an example of the proof of theorem 2.7. Now, what we're talking about is the inverse of a matrix. So the inverse of a matrix is given this symbol, a to the minus 1. That doesn't mean 1 over. It doesn't mean it. What it does mean is inverse. And in a sense, it is a multiplicative inverse, but it's not a reciprocal. That's only good for numbers and variables, reciprocal. Just like for functions. The inverse of a function is not the reciprocal of the function. It's the function that undoes the other function. Okay, so that's what inverse means more here. So the inverse, A inverse of an invertible matrix A okay, is unique. That's what we just showed. So you can call it the inverse of A, and then you can just say, as I've been writing right up here, A times A inverse is equal to A inverse times A, and that's equal to the identity matrix of that size. Okay, back off just a moment. The only matrices that even have a chance of being invertible are square matrices. If it's a rectangular matrix that the n and m are not the same, no way. It will not have an inverse. It's non-invertible. Okay? So you have to be square, but being square isn't enough. It has to be invertible. Okay. So, sorry, we worked outside burning a bunch of brush and trash and stuff like this over the weekend. I think I breathed too much smoke, so I'm just gurgling almost, so I hope this will clear up in time. It's not as bad today as it was yesterday, so hopefully it'll get better. So, here's example 1. Show that B is the inverse of A, where A is equal to -1, 2, -1, 1, and B is 1, -2, 1, -1. Okay? How are you going to show their inverses of each other? What would be a good way to do it? Multiply them together and see what you get. So let's do AB. Of course, that'll be a 2 by 2. And what do we get? I'm sorry? One for the first entry. The 1, 2 entry will be 0. The 2, 2 entry, 2, 1 entry will be 0. And the 2, 2 entry will be 1. Hey, that's the I. But that may not be enough. We also need to show what BA is. So let's rewrite A over here as -1, 2, -1, 1. And let's do what BA is and see what that gives us. Okay, 1, 1 entry here would be 1. 1, 2 entry would be 0. 2, 1 entry would be 0, and 2, 2 entry would be 1. Perfect. Yes. That's also the identity matrix, 2 by 2 identity matrix. So yes, these two have to be inverses of each other. If those two conditions are met, then they are inverses. Okay. Now, this next example shows how you get them. They just gave them to us. How do you find them for yourself? So here's, I think I'll clear the page. All right, anyone need this any longer? Okay. Here's matrix A. 1, 4, -1, -3. Okay. To find the inverse of A, solve for the matrix. We know that, let's just say, let matrix X equal A inverse. Okay? Then we know that A times X would have to equal I, right? Agreed or not? Okay? Now, if you're trying to solve for matrix X, then, well, let's just do it. This will be, let's just let X be X of 1, X of 2, X of 3, and X of 4. You okay with that? They do 1, 1, 1, 2, 2, 1, and 2, 2. You can do it any way you want to. We'll do it the way they did. Okay? So this will be 1, 4, negative 1, negative 3 times X of 1, 1, X of 1, 2, X of 2, 1, X of 2, 2 equal 1, 0, 0, 1. Agreed? What you think? It would have to be the case, right? Okay, so let's do it to it. Let's multiply these two together. What do you get? Do your matrix multiplication. It's going to be a square matrix, right? What would be the first entry? Okay. Next entry would be got it. Next. Two, 1. All right. And the last would be goodness. Okay. My minus sign went all over the place. Whoa, no, that wasn't my minus sign. That was the bar that I was writing on, so it's okay. Still all over the place. And that has to be equal to 1, 0, 0, 1. All right. Now let's take this item by item and write down those equations. X of 1, 1 plus 4x of 2, 1 is equal to 1, right? Next one would be x of 1, 2 plus 4 x of 2, 2 is equal to 0. The next one would be minus x of 1, 1 minus 3, whoops, got out of place, minus 3x of 2, 1 is is equal to 0, and minus x sub 1, 2, minus 3 x sub 2, 2 is equal to 1. Agreed. Yay or nay? What you think? Okay. Now, actually, these two right here are one system of equation, and these two are in another system. So I probably should have written it that way. X of 1, 1. No, I said it wrong. These four here are one system, and these four here are the other system. So x of 1, 1 plus 4x of 2, 1 is equal to 1, and minus x of 1, 1 minus 3x of 2, 1 is equal to 0. Okay? Just add those two together and you get x of 2, 1 is equal to 1, right? And then plugging that in here, four times 1 is equal to 1. So this would be x of 1, 1 plus 4 is equal to 1. So x of 1, 1 is equal to negative 3. Okay? So x of 2, 1 is 1. X of 1, 1 is negative 3. And take the next pair, x of 1, 2 plus 4x of 2, 2 is equal to 0, and minus x sub 1, 2 minus 3 x sub 2, 2 is equal to 1. Add those two together and you get x sub 2, 2 is equal to 1 again, which is what we got, they got. And then plugging that back in either place, I'm going to put it here, x of 1, 2 plus 4 is equal to 0, so x sub 1, 2 is equal to minus 4. Okay? So basically, your x matrix, which is your solution matrix, which we are going to claim to be the inverse matrix, is minus 3 minus 4 1 okay, I'm getting lost here. 2, 1 is 1, and this is 1. Okay, there we have it. Okay, and that's what they got. Now, they claim, and we do too, that this is your A inverse. It's the X matrix, but it's also our A inverse. Okay, it says U matrix multiplication to check the result. Let's just do that quickly if we can. Should be, because that's how we got it. Minus 3 plus 4 is 1. minus 4 plus 4 is 0. 3 minus 3 is 0. And 4 minus 3 is 1. Yeah. That is the identity matrix, so that works. Somehow a couple of little swirly little lines made it on the board. They don't belong there. Okay. Now, generalizing the method we just did, okay, provides a convenient way for finding an inverse. And note that the two systems of linear equations, when we wrote them like this, okay, have the same coefficient matrices. 1, 4, negative 1, negative 3, 1, 4, negative 1, negative 3. Okay? Same, identical coefficient matrix. That's where they came from. Okay? Excuse me. Now, I did it by elimination by addition. What you could have done is this. Gauss-Jordan elimination. 1, 4, 1, negative 1, negative 3, 0. Or 1, 4, 0, negative 1, negative 3, 1. Okay. Now, yeah, those would be, and you solve those simultaneously. I mean, just solve them. Okay. Separately. Okay. But guess what? Since these are the same as that, those two are the same, you could have just, running out of room very, very fast. So I think I'll erase this upper left. I thought I would. My eraser is very, very slow. Okay, done though, finally. Well, it didn't come back. Still didn't come back. There we go. What you could have done is this. 1, 4, negative 1, negative 3, and then done 1, 0, 0, 1 here, and solve those simultaneously. Okay? It would have saved the writing. The steps would have been the same. But if you had done this elimination, you wound up with 1, 0, 1, 0, 1 here, and your solutions here, which would be, oh, I erased it. Here, negative 3, 1, and then this would have been 0, negative 4, 1. Okay, that's what that would have wound up being had you solved those, because that's what we did. We got those numbers. So if you did this, what you would have gotten, because in solving this, you wind up with the identity matrix 1, 0, 0, 1, and then you would have gotten this as the other side, negative 3, 1, negative 4, 1. Okay? And that would have been your inverse, A inverse. Okay. Now, what that's saying to you is, if you have a square matrix and you want to see if you can find an inverse, then you take the square matrix that you got, do row reduction with this on your identity matrix. So adjoin to the matrix, your square matrix you're doing, the identity matrix of that same size, do your row reduction till you get this to look like your identity matrix, and what you wind up with here is your A inverse. Now, hint, if you wind up with something that doesn't work, then you know the inverse doesn't exist. That's one way of telling. We'll find other ways of telling, but that's one. Okay? So I guess they actually want us to do Gauss-Jordan. So let's do it. We're not used to doing it in this context, but we'll do it in this context. And it's not a bad thing to do. Okay? All right. What's the first thing we want to happen if we're reducing this? What's the first thing we want to happen? A 1 right there, and we got it. Next thing we want to happen? 0 below it. How are we going to get that to happen? Yeah. Row 1 plus row 2, or row 2 plus row 1 is the new row 2. So that would be, keep the first row as it is, 1, 4, 1, 0. And then this will give you 0, 1, 1, 1. Okay. So, we got 1 here, 0 is below it. Next thing we want is a 1 there. We want a 0 above this. Gauss-Jordan. So how do we get like that happen? Okay, I'm going to have to create some more room here. I wish my eraser were faster. Okay, I think we got it. And what you said was minus 4 row 2 plus row 1 is the new row 1. That's what you said, right? Okay, so we're using the bottom row 0, 1, 1, 1, which is exactly what we want it to be. And the new top row is going to be 1, 0, negative 3, negative 4. And that's exactly what we got here. There's your A inverse. So this is how it works. If you start with AI and do row reduction, you should want to I A inverse. And that's sure enough what we got in this case. Now this procedure or algorithm works for an arbitrary n by n matrix. If A cannot be row reduced to IN, then A is non-invertible, or the other word for it is singular. Those two words mean the same, non-invertible or singular, therefore their opposites are the same too, invertible or non-singular. Okay. Says the procedure will be formally justified in the next section after introducing the concept of elementary matrix. And for now, a summary of the algorithm is shown below. Now, Do both of you have your books? You have? You do? Josh? You don't. Okay, so let me write this down for you. Okay. Find the inverse of a matrix by its Gauss-Jordan elimination. So A has to be square. Has to be square. If it's not square, there's no way it'll have an inverse. We'll say of order n. Okay, meaning it's an n by n matrix. Okay. Now, step 1. Write the n by 2n matrix that consists of A on the left-hand side and I sub n on the right-hand side. It's an adjoint matrix of matrix A, which is n by n, by the identity matrix n by n as well. Okay? So that's what you got to begin with. This process is called adjoining matrix I to matrix A. That's adjoining the matrices. Number 2. If possible, row reduce. Okay? And what we want to let's see, I'm trying to think of my terminology now. To reduced row echelon form. So row echelon form would be ones on the diagonal and zeros below it. Reduced row echelon form would be ones on diagonal and zeros above and below it. Okay? So if you are able to do that, then what was A will now be I. And then whatever the result of I operating, and that's I sub n as well, that will be your A inverse. Okay. If that's not possible, then A is non-invertible or singular. And then they say check the work by doing A times A inverse, and also making sure that's the same as A inverse times A. And if they are the same, that should be I in both cases. Now, they talk about linear algebra applied here, and they go back to Hooke's law, which states that for relatively small deformations of an elastic object, the amount of deflection is directly proportional to the force causing the deformation. Okay? In a simply supported elastic beam subject to multiple forces, the deflection D is related to the force W by the matrix D is equal to F times W, where F is the flexibility matrix whose entry depends on the material of the beam. The inverse of the flexibility matrix, F inverse, is called the stiffness matrix. And exercises 61 and 2 will you'll be asked to do something with that. Now, frankly to me, that sounds like materials engineering. So if that's in either of your future, you may see things like that. All right. Moving on to example 3, and this one you can see larsonlinearalgebra.com for an interactive version of this type of an example. All right, this is biting off a bigger chunk here. Find the inverse of this matrix A. 1, negative 1, 0. 1, 0, negative 1. And negative 6, 2, 3. Okay. How would we proceed? What would be our next step? somebody? What would you do? Okay. Adjoin this matrix with the appropriate I matrix. What I matrix would that be? 1, 0, 0. 0, 1, 0. 0, 0, 1. Okay. Where would you start now? What's the first thing you want to happen? And we got it. Okay, so we didn't have to do a thing. What's the next thing we want to happen? 0 below it. How will we make that 1 below it become a 0? Negative row 1 plus row 2 is the new row 2. Okay? So we're using row 1, write it down. 1 minus 1, 0, 1, 0, 0. Okay? What's your new row 2? 0, 1. Nice. Negative 1. Negative 1. 1. 0. All right. What's the next thing you want to happen? Okay, how do you make that happen? Second? 6 times row 1 plus row 3 is the new row 3. Okay, so what will that be then? 0. Negative 4. 3. 6. 0. 1. All right. What's the next thing you want to happen? Row 2, the first non-zero entry to be a 1. And we got it. We didn't have to do a thing. It's already there. After that, what? We certainly do, but even before that, 0 above the 1. So how will we get that one to work? Okay. Row 2 plus row 1 is the new row 1. Okay? So we're using row 2, so write it down. 0, 1, minus 1, minus 1, 1, 0. Okay? New row 1 will be 1, 0, negative 1, 0, 1, and 0. Okay. Now, what you were saying before, what do we want next happen? And how does that happen? Got it. Okay, and what does that give us? 0, 0, negative 1, 2, 4, 1. All right, what's the next thing we want to happen? In row 3, first non-zero entry, you want to do that? I'll do that this way. Plus, minus, minus, minus. You okay with that? I'm really lazy. Okay, what's the next thing you want to happen? Okay, the zero's above that, and how do we make that happen? Okay. Row 3 plus row 1 becomes the new row 1, and row 3 plus row 2 becomes the new row 2, right? Okay, so let's do it to it. We're using row 3 now, so that's 0, 0, 1, minus 2, minus 4, minus 1. That row should not change anymore. So that's the bottom row of your identity of your inverse matrix, those last 3 digits, if this is invertible. Let's see if it is. Let's do row 1 first. What does that give us? 1, 0, 0, negative 2, negative 3, negative 1. New row 2 is 0, 1, 0, negative 3, negative 3, negative 1. So, our suspicion, we hope is true, is this is your A inverse. How do we check that to see if it is true? Multiply it by A. Now that's going to be sort of a pain in the neck, but let's do it here. That's 1 minus 1, 0. 1, 0 minus 1. Negative 6, 2, 3. Multiplied by negative 2, negative 3, negative 1. Negative 3, negative 3, negative 1. Negative 2, I can't write. Negative 4, negative 1. Sort of unusual to have all negatives there, but weirder things could happen. These are certainly multipliable, so that's going to be a 3 by 3. Okay, let's start. What do we get? Anybody? Multiply these two together. These give you negative 1. This is minus 2 plus 3, 1. Yeah. That's a 1. That's good. We didn't want that to be a negative 1. Next entry. Well, you say that. Is it true? Negative 3 plus 3 is 0. Next entry. Second. 0. Next entry. Zero. That's good. Next entry. One. Good. Next. Zero. Good so far. Next. Ooh, big numbers. Zero. Next. Even bigger numbers. Zero. Okay, and the last. 1. Now, I know you're hankering to do it the other way, too. I am, too, really, but I'm just going to try to resist the temptation to give myself that much pleasure and just let it go like this. It says, confirm this by showing that A times A inverse is equal to I, which we just showed, and the A inverse times A is I. Notice how they leave that to the student. Okay. The process shown here applies to any n by n matrix, and we'll find the inverse if it exists. When A has no inverse, the process will also tell you that. The next example will do that. So let's move on to the next example. All right. What we got, about 15 minutes? 11. Okay, let's see if we can get this done. I think we can. Here's a matrix A, 1, 2, 0, 3, negative 1, 2, negative 2, 3, negative 2. I hope I wrote it right. What will we adjoin that with? Which is? Which is? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. First thing we want. 1 in upper left, we got it. Next thing we want. Okay, so how will we make that happen? All right, and that will give us our new row 2. So do it. Oh, we're using the top row, so it's 1, 2, 0, 1, 0, 0. Okay. Using that one, what's your new row 2? 0, negative 7, 2, negative 3, 1, 0. Okay, what's the next thing we want to happen? Okay, how will we make that happen? Got it, is the new row 3. Okay, so what will that give us? 0. 7. Negative 2. 2. 0. And 1. Okay. Now, do you sense something coming up here? Okay, you like to work hard, I can tell. Okay, here's I wouldn't yet. Here's what I would do right now. Noticing these two. Let's just add these 2 rows together. What would that give you for your new row 3? 0, 0, 0, and equal something that's not 0. That will never become an identity matrix because it's got to be 0, 0, 1. That came out 0, 0, 0. Not going to happen. This does not have an inverse. This is This is a singular matrix, a non-invertible matrix, because there's no way you can get an identity matrix here with those numbers. Now, you could do what you were going to say, and that would work, but just as soon not. As soon as you can see that's not going to happen, stop it. In its tracks, okay? Now, and I didn't even write the rest of it down, but the A portion has a row of all zeros. No way you'll get that to be an I. It has a little blurb here saying using Gauss-Jordan elimination to find the inverse of matrix works well, even as a computer technique. You can program a computer to do this for you because everything's pretty regular here. For matrices of size 3 by 3 or greater. For 2 by 2 matrices, however, you can use a formula for the inverse rather than Gauss-Jordan elimination. Okay? Do we have time for this? What time is it?
6 minutes.
6 minutes? Oh, I think we do. Okay? So, if A is a 2 by 2 matrix, A, B, C, D. We usually don't name them like that, but if we do, then A is invertible if and only if, that symbol's recommend that, get this, AD minus BC is not equal to 0. It's invertible only if that's true. Now, where do we see something like that? Was it in this course, or that was the other course, wasn't it? When we're doing cross products. What do we call that? A determinant. 2 by 2 determinant. AB minus BC. AD minus BC or CB, however you want to call it. Okay? Now, that's chapter 3. We haven't done determinants yet, but we're just doing one here. Okay? If that determinant is not equal to 0, this is invertible. Okay? Now, if that AD minus BC is not 0, then the inverse of A, it will be invertible, will be 1 over that determinant, AD minus BC, okay, times, not the original function. But notice what they do. Now this seems like there's a lot of moving parts here, and there are. But here's what we do. On the main diagonal, reverse them. Make this D and this A. And on the upward diagonal, negate them. Negative C, negative B. Okay? And then when you do that, you get the inverse matrix. Now they did this without proof. They just said, hey, this will work. Okay? And you'll deal with determinants in the next chapter. But this, believe it or not, is a shorthand, for how you do a 2 by 2 matrix. It doesn't work for anything any bigger, so don't even try it. But you see, the thing that makes it good is if you just do this, you'll find out whether it's got an inverse or not. If that thing's 0, it doesn't. If it's not 0, it is. Well, if it's not 0, just put it in the denominator. Whatever that is, put it in the denominator. And then remember to reverse the main diagonal and negate the upper diagonal. And then multiply that out. You got it. That will be the inverse every time. And that is shorter than Gauss-Jordan elimination. Probably not by a whole lot, but by a little bit. Okay? You don't have any row reduction to do at all. So We'll see. How much time now?
3 minutes.
Huh?
3 minutes.
3 minutes. Well, let's do A then. I didn't think we had that much time. Okay, let's see. While it's fresh on our minds, let's do, here's matrix A. 3, -1, -2, 2. First question, does it have an inverse? What's your determinant?
76 minus 2.
Yep, is 4. So A inverse, it does have an inverse. We know it does. It's going to be 1 over 4. Just whatever that determinant was, put it in the denominator. And then what will be your matrix you multiply that by? Do main diagonal first. 2, 3. Do the main diagonal. Now do the upper diagonal. Nope, you negate it. What's that? Okay. Your main diagonal, your main diagonal you reverse, and your upper diagonal you negate. Okay. Now let's multiply those out and see what we get. Okay. Frankly, I don't like doing that. Let's just leave it the way it was. If it's all right with you, since I've got it written this way, I'm just going to multiply this by our A, because it should work either way, right? 3, -1, -2, 2. So let's multiply those two together and see what we get. Four. 0. 0. 4. Oh, I left off my 1/4 in front. Guess what that gives you? Okay. Only because we don't have enough time, I'm not going to do it the other way. Okay. But it's just so much easier to multiply the whole numbers and then multiply with a fraction later than doing that. So next time we'll start with the B. Okay. Part here. All right. Let's give you a few homework exercises to do. All right. We've made decent progress here. I think you can do any of the odds 1 through 5. They're all at Calc Chat. Then I think you can do any of the odds 7 through, 29. Now 27 and 29 are 4x4s. They're going to take a lot more effort to do. They suggest you use a utility to do those. You might be able to do them without, especially 29, because it has quite a few zeros in it, but that doesn't guarantee anything. 25 is also a 4x4, but it has a whole bunch of zeros in it. So looking at 25, do you think that's going to have an inverse? Things that makes me suspicious is that third row, all zeros. I would be surprised, but I may be wrong. Okay, but anyway, for sure try to do some of the odds 7 through 23 anyway. 25 shouldn't be too bad. Okay, and then 33 through 35, you can try those two now that you know, got the new technique, and we'll stop there and pick up the rest of them later. Good deal.
Question
Okay,
involving calculus 3
involving what?
for the test for calculus 3.
Oh, okay.
Is that like a lot way off?
Wow. Okay.
I know in the for the unit vector orthogonal, you have to do the cross product, and then it's cross product over the magnitude of the cross product.
Yeah. And a quick check would be, is this squared plus that squared plus that squared equal to the denominator? It is. You have checked that. So you know it's a unit vector. I don't remember the number being that big, okay? I'm not saying it isn't. It's been a long time. I didn't even look at the key this time. But
Another big number.
I don't have it up here with me, so I can't check it.
Yeah, I mean, it is.
Okay. Yeah. Yeah. What a nasty mess. Didn't realize, I didn't remember because it's been so long. Okay, I'll take your word for that one. Take your word for that one. Take your word for that one. Okay, if I'm not wrong, these are both minuses, right? Oh, yeah.
Mm-hmm.
Yeah, okay, so that's okay. That's this one, yeah. And that looks okay. That looks okay. Yeah, they sure are some big numbers. It looks like you're doing right. I just didn't remember.
Yeah, I was wondering. I was like, oh, it's huge
I know.
numbers.
If you want to go down to my office, because I've got to go down and grab a spot of lunch, we'll look at that. Let me get this stopped up.